Alright, welcome to section 7.3. Today we're going to kind of combine 7.1 and 7.2 together to talk about how we can use exponentials and logarithms to help us problem solve. So we're going to start things off easy with just some simple examples, but then we're going to get into some word problems where exponentials and logarithms are used quite heavily. So before we dive into some of the examples, let's just quickly review some properties of equality. In terms of exponential equations, remember that's when we have a variable in the exponent position, very similar to how these are written. Notice how if these two pieces have to be equal to each other, that means every single piece must be equal to each other. So if the bases are already equal, notice how they're both already b's, that means our exponents must be equal as well. So in other words, x would have to equal y. The same thing goes for logarithms, because remember logarithms are essentially exponentials as well. Notice how the log has the same base on both sides, so if they are equal to each other, that means the quantity of the log that we are taking must be equal as well. Again, in other words, x would have to equal y. Now, some basic things to kind of remember about these two different properties of equality is that our bases in either case, either for exponentials or logarithms, have to be bigger than 0, but the base cannot be 1. Because if we were to take 1 to any power, our answer would just simply stay a value of 1. So we have to have a positive number, okay, bigger than 0, but we cannot be 1. That essentially means that we can have fractions, because those are bigger than 0 and not 1, but then we can also have numbers, any number you want to pick, greater than 1. Alright, so let's start things off here with our first example. We're going to solve, this example by equating exponents. Equating meaning eventually equaling them together. So if we eventually want to get our exponents to equal each other, that means our bases have to be equal to each other. We're using that idea of equality here. If we want our exponents to be equal, okay, if we want x and y to be equal, then our bases have to be the same as well. So let's somehow figure out how can we get a base of 16 to be written the same as a base of 1 over 4. So again, you might remember this back from 7.1. We got to try to think of a number that both 4 and 16 would have in common, but in terms of using exponents. So in other words, we can rewrite 16 as a base of 4 to a power of 2. Because 4 squared would give us the 16. So we're just rewriting the base of 16. We're not really doing anything with the exponent yet, so that will just stay the same. Now over here, how can we write 1/4 with a base of a positive 4? Well, notice how if 4 is in the denominator, that means that the power would have to be negative. In this case, it would be a -1. And again, we didn't really do anything with this exponent yet, so that's just going to stay the same. So now our bases are the same, we can somehow combine or do some things with our exponents. Notice how we have a power to a power. So using our property of exponents, we can multiply those powers together. That would give us a 4x plus 6. Okay, we got to distribute the 2 to both of those terms. And same thing over here, we have a power to a power, so we can distribute the -1 as well. So now notice how we have the same base, which means that our exponents must be the same as well, since we have them being set equal to each other. So 4x plus 16 should equal -7x plus 1, and from there it should be pretty simple for us to solve. So maybe I'll add the 7x over, which would give us 11x plus 6. If I subtract the 6 over, I'll be left with a -5, and dividing by 11, we finally get -5 over 11. There we go. So what I want you to do is pause the video and try number 2 on your own. Remember, our goal is to somehow get the same base, that way we can just focus on those exponents. Alright, so let's check it out and see how we did. Between a 25 and a 125, both of those can be written as a base of 5 to a power, because 5 squared would give us 25, but notice how 25 is in the denominator, just like this 4 was, so that means our power is negative. So instead of 5 squared, we would need a 5 to the -2. Now over here we can rewrite 125 as 5 cubed. So right there we're starting to get the same base. So on the left side, when we have a power to a power, just like we had in our first example, we can multiply the powers together. We would have to distribute in this case, and we would get 6m minus 2. So now that our bases are the same, they're both 5s, we can focus on the exponents, and they should be equal as well. Since the bases are the same, the exponents should be the same also. So we can add the 2 over to get 5 and simply divide by 6 to get a value of m of 5 over 6. Alright, so let's move on to some examples where using those property of equalities like we did in the last two examples may not work. Okay, in these cases we're going to have to eventually take a logarithm to help us solve these equations. So notice how both of these are exponential equations. We have a variable in the exponent position. So our goal, if we want to try to figure out the value of x, if x is in that exponential position, let's isolate the exponential, meaning we want to get the base and the exponent all by itself. Okay, so on this side, if we're trying to isolate this piece, get 10 to the 6x all by itself, we somehow need to move this multiplication of 11 to the other side. So if we want to move a multiplication of 11 to the other side, we can divide both sides by 11. That way these go away. So notice how just our exponential piece, our base to our power, is by itself, and over here we would have a value of 5. Now this is where what we did in the last two examples might not work, because there's no possible way, at least an easy way, to rewrite 10 and 5 that have a common base. Okay, if I go back for a second, it was really easy for us to rewrite 16 and 4 as a common base, and really easy to rewrite 25 and 125 as a common base, but we can't really do that here. So this is where a logarithm is going to really help us solve for x. Now in the last lesson in 7.2 when we talked about logarithms, it is possible for us to convert between exponentials and logarithms. So if this is currently an exponential, let's turn it into a logarithm to help us solve it. So notice how in this exponential our base is 10, so that means the base of our log should be 10. And logs are always equal to exponents, so this 6x should be on the other side, should be equal to 6x, and then our value of 5 is what we would actually take the log of. Okay, so we have a base, logs are always equal to exponents, and our answer, if you will, because notice how it equaled 5 in this this step right here, is what we take the log of. So what we can do is try to figure this out actually. If on your calculator, if you take log base 10 of 5, I believe you get 0.69897. And then when we divide by 6, we get 0.116495. Okay, so there's a way, even though we were not able to convert the bases to a common base, we can still solve for x in the exponential position by taking a logarithm. Because remember, logarithms and exponentials are inverses of each other. So if we start with an exponential and we use the inverse, okay, in other words, a log, to help us solve it, we should be able to get an answer in the end. All right, let's try one that's a little bit more complicated. Again, let's isolate the exponential. So we just want to get the base and the power all by itself. So in this case, we got to move over the 7 and also the 9. So let's do maybe each step individually. If we subtract the 7 over, we'd be left with 90. And then if we divide by 9, we'll be left with 10. So notice how our exponential is all by itself, the base and the power alone right there. And again, there's no really easy way for us to make 14 and 10 into a common base. So let's use a logarithm to help us solve for x. In this case, our base is 14. Our answer, if you will, is 10, so that's what we take the log of. And logs are always equal to exponents. So our exponent in this piece was 9n plus 8. So on your calculator, if you were to try to find log base 14 of 10, I believe you get 0.8725. And from there, we have simple algebra to solve for n. When we subtract 8, we get negative 7.13. And when we divide by 9, I believe we get like negative 0.79 for our answer for n. Alright, so instead of starting with exponentials like we did in the last two examples, now let's actually start with a log. So in the last two examples, notice how when we started with an exponential, that's what we wanted to get all by itself. That's what we wanted to isolate. But in this case, since we're starting with a logarithm, let's isolate that piece of our equation. So if we're going to isolate the log, in this case it's a natural log, let's move over the 5. We can add over the 5 to get 9. Now again, now that the logarithm is isolated, we want to use the inverse to help us solve. Just like we added 5 to both sides, we had to use the inverse. Addition is the inverse, or in other words, opposite of subtraction. So if we're trying to solve this, we want to use inverses. The inverse of a log is an exponential. So let's turn this logarithm into an exponential equation. When we have a natural log, okay, that means we have a base of e. So I have a base of e. Logs are always equal to exponents, so this 9 is an exponent on this base. And whatever we're taking the log of, that's what our exponential should equal. In this case, it's kind of our answer, if you will. So now that we can we can actually solve for x. We can add the 6 over, and we can let our calculator do the rest. If you were to take e to the 9th and add 6, I think you get something like 8,109.08, something like that. But notice how we're just using inverse operations. If we start with an exponential, like we did in the last two examples, we have to change it to a log. But in this case, since we're starting with a log, we eventually have to change it to an exponential. Alright, so let's try another one. Since we're starting with a log, let's get that piece all by itself. So we would have to move over the 7. When we subtract 7, we'll get negative 10. Alright, so now that we have the log all by itself, let's convert it into an exponential. We would have a base of 2, a power of negative 10, because logs are always equal to powers, and our answer, if you will, would be b. So this one's pretty simple, okay? Notice how our variable is kind of all by itself. We just got to figure out what 2 to the negative 10th would be, and that's a really, really small number. I think it's like 0.000976556, something crazy like that. So that one really wasn't too bad. Let's try one that's a little bit more complicated. Again, if we're starting with a logarithm, let's isolate that log piece, get it all by itself. So we would have to, in this case, move the 5 over. Okay, we can add that to the other side, and we'd be left with negative 7. Lastly, we got to get rid of this negative 7 that's being multiplied out front, so we can divide that over as well, which would give us 1. So now that we have the log all by itself, we can change it from a log to an exponential. Our base is 3, our power is 1, and our answer would be n minus 10. So 3 to the first is just 3, and if we were to add 10 over, our solution for n would be 13. So it kind of looks complicated when you first look at it, but really not that bad. It's just simple algebra steps with just a little conversion in the process. Alright, so what I want you to do is pause the video and use all of your powers in the logarithmic universe to try these two on your own. I'll be back in a little bit to see how you do.
Downtown, 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 downtown. She has her arms around your waist, with a balance that will keep her safe. Have you ever felt the warm embrace of a leather seat between your legs?
so let's check it out and see how we did. For number 8, notice how we're starting with an exponential. We have a base to a power, so let's isolate that piece right there. So we could subtract the 7 over, which would give us a -5, and then when we divide -3 over, we're left with a positive 5/3. So now that our exponential piece is all by itself, we can convert it into a logarithm. Okay, we're using those inverse operations to help us solve. Now, since it has a base of an e, that means we'd have to use a natural log. So we would have a natural log of 5/3, and that should always equal our exponent, because logs always equal exponents of this -x. So you might need to use your calculator for this piece. We get 0.5108 about equals our -x, and moving the negative over gives us a -0.5108. So for number 9, I decided to show you kind of 2 different ways to do it depending on which method you used. Again, we're starting with an exponential, so our first step should always be to isolate that. So no matter what, we would have to divide the 32 over. 2 divided by 32 gives us a 1/16. So from there, there's kind of 2 different ways you could have gone about this. Maybe you found a common base, which is absolutely possible, because notice how this is a 4 and this is a 16. We can rewrite those numbers with a common base. But maybe you didn't really catch that and you decided to do logarithms. Okay, I'm going to go over both pieces. So if you decided to do a common base, we can rewrite 1 over 4 as 4 to the -1st, and we can rewrite 1 over 16 as 4 to the -2nd, because 4 squared would give us 16, but since it's in the denominator, we know the power would have to be negative. So on the left-hand side, we have a power to a power. We can multiply those together to give us a -x divided by 3. And now that our common bases are both 4, we know that our exponents should equal each other. So we get -x over 3 equals -2. Solving from there, okay, we can multiply the 3 over to give us a -6. So our final answer would actually be a positive 6. But maybe you decided to use logs. So in this case, just like kind of over here on number 8, in this exponential, if we wanted to solve it, we could transform it into a logarithm. We have a base of 1/4. We would have to take the log of a 1/16 because logs always have to equal exponents. So our power, this x over 3, would have to be on the other side of the equal sign. So this piece right here, you could use your calculator to help you out. Log with a base of 1/4 of 1 over 16 would give us actually 2. So when we multiply the 3 over to solve for x, we get the same answer of 6. So really, in this case, you could have used either ones. You were able to use a common base like we did, but maybe some of us decided to go straight for logarithms because that's what we kind of did in the last few examples. Either way, you're good to go. Alright, so now that we're kind of getting used to solving exponential and logarithmic equations, I want to dive into some examples where we actually do need to solve exponentials and logarithms in real life. So in your notes, you have a bunch of these different formulas. Newton's law of cooling, dealing with temperature. We got decibel levels, dealing with sound. Richter, or earthquake intensity or Richter scales, dealing with earthquake sizes. We also got rocket science, half-life decay, kind of used in biology. Same with carbon dating. And the last 3 towards the bottom are ones we've already kind of looked at. We talked about compound interest, growth and decay models, as well as continuously compounded interest, I believe in section 7.1. So I will always give you these formulas, okay? I don't expect you to memorize them, but what I want you to do is be able to use it, okay? If I were to give you a formula and tell you what each piece actually means, can you solve a problem? Okay, can you use the formula to help you out? So that's what we're going to take a look at in these last few word problems. So looking at number 10, we have myself visiting the New York Metzgerie for Miss Petrek's special Corey dogs. We know the dogs are cooked at 325 and the room temperature is 72 degrees. From the moment the Corey dog comes off the grill, we wait 2 minutes and then we decide to measure the temperature to be 205 degrees. how long after taking the dogs off the grill should I eat it? Okay, because 205 degrees might be a little hot. Notice how I kind of told you that 120 degrees is a safe temperature to eat food. So we got to let the Cory dog cool a little bit. In this case, since we're talking about temperature, we want to use Newton's law of cooling. So that's this bad guy right there. And I tell you what each piece actually means. Okay, so go ahead and look at those different pieces, what these different variables actually mean. Alright, so after you take a look at what these different variables actually mean, we can go ahead and use the information given to us and kind of plug in the stuff we know. Okay, T, or capital T of little t, is the temperature of the object after a certain amount of time. So they kind of told us here after 2 minutes the temperature was 205 degrees. So we actually can put 205 into this position, and notice how the time we're specifically looking at is 2, so we can put 2 in for that little t value right there. Now they also told us that T sub S is the temperature of the surrounding environment, kind of meaning the room temperature, okay, the air temperature, and they told us that was 72. So we can put that in for T of S in this position as well as this one, okay, it kind of shows up twice. Then T sub 0 is the initial temperature of the object. So the moment we take it out of the oven, it is 325 degrees. So we can put that in for T sub 0. And notice how the only piece we don't really know is that constant. Okay, this is, back when we talked about variation, we had that constant of K we had to use. The same thing's going on here. This constant is going to change depending on the material or the scenario that we're talking about. So when we find the value of K in this example, it may not be the value of K for a different example or word problem later on. Okay, this value of K is going to change. But notice how if that K is the only piece we don't know, we can actually go ahead and solve for it. Notice how this equation is exponential. Okay, the position or the object, the variable we're trying to find, is in the exponent position. So we want to isolate this exponent. So let's clean this up a little bit. We can actually add or subtract those two pieces together. 325 minus 72 is 253. And I'm going to rewrite this as negative 2k instead of k2. So if we want to isolate this exponential piece, let's subtract 72, which would give us 153. And then we can divide by 253. To give us about 0.52569. Alright, so now that our exponential is isolated, it's all by itself, we can convert it to a logarithm. Now since our base is e, okay, we need to use a natural log of 0.52569, and logarithms always equal powers, so this should equal negative 2k. So this piece we might have to use our calculator. I believe we get negative 0.643. And if we were to divide by negative 2, our k value is 0.32152. Alright, so that's a k value, useful to know, but notice how it does not answer our question. How long after taking the dogs off the grill should I eat it? So we're actually trying to figure out a time in this case, not the constant. But now that we know the constant, just like we talked about for variation, we can plug this constant back into our equation. So notice how, in this case, we're specifically looking for an ending temperature of 120. Okay, that's when it's safe. So our new ending temperature we want to focus is 120, okay, instead of this previous ending temperature of 205. Our room temperature is still 72. The Cory dog was still 325 when it got out of the oven. We have a base of E. We found our constant. Okay, we have a negative 0.32152. Okay, it's negative because that's what it looks like in the equation. Even though our K was not negative, okay, it is negative in the equation, and we're trying to figure out how long do we have to wait in order for it to be this temperature of 120. So what I want you to do is pause the video and kind of go through this process again to help you solve for T. Alright, so let's check it out and see how we did. Our steps here should be very similar to what we did over here, okay, but instead of solving for k, now we're solving for t. Okay, very similar, just a different variable, but notice how they're both in the exponent position. So the work should be very similar. We can subtract the numbers like we did before to get that 253. Again, we want to isolate the exponent because that's where our variable is, that's what we're trying to find. So we can subtract the 72 over to give us 48. And then we can also divide both sides by 253 to give us 0.1897. Okay, that way our exponential piece is all by itself. So now that our exponential piece is isolated, let's convert it into a natural log. Okay, we're still using those inverse operations to help us solve. With a base of e, we can have a natural log of 0.1897, and that should equal our exponent, what we have right here. So the natural log piece, you may have to use your calculator to help you figure that out. And once you get that number, you can divide this coefficient of negative 0.32152 over to give you roughly about 5.17 minutes. So we gotta wait a little bit more than 5 minutes. That way it is safe to eat this Cory dog. Alright, let's check out our next word problem. The atomic bomb dropped on Nagasaki in 1945 released about 1.34 times 10 to the 12th joules of energy. Good golly, that's a lot of energy. What would be the magnitude of an an equivalent earthquake that released that much energy? So we gotta figure out what's the magnitude, okay, what's the strength of that earthquake. So we're going to use the earthquake intensity Richter scale, this little formula right there. Again, I tell you what each piece means. I want you to be able to use this with this information as well as the information in the word problem to answer the question. So M is the magnitude of the earthquake. Notice how that's what we're trying to find. Okay, so we'll just leave that as M. So we need 2/3 times the log. Okay, it doesn't really give us a base, so we can assume the base is 10. Okay, you can write that in there if you want to. And we got to fill in these two missing pieces. Now they tell us E is the energy released by the earthquake, or in this case the bomb, which would be 1.34 joules of energy. Now we're trying to figure out what would an equivalent earthquake be. So if the bomb had this much energy, the equivalent earthquake would have that much energy as well. So we can write 1.34 times 10 to the 14th. And then E sub 0 is always this. Okay, well that was pretty easy. E sub 0 is always 10 to the 4.40 joules. So really this is almost turning into a calculator problem. Kind of gave you an easy one here. We can simplify this piece. Actually, let's go ahead and use our calculator. I don't know what I'm talking about. I'm just going to type everything in the way I see it. So let's bring up our calculator. Alright, so our equation was 2/3, I'm going to put that in parentheses, times the log base 10, so we don't have to worry about going into math and selecting that log base option. Okay, this log option directly on your calculator is a base of 10, so we can just hit that log. And we want to do this top portion divided by the bottom portion. So since I'm dealing with a fraction, I'm going to go ahead and write this in parentheses as well. 1.34 times 10 to the 14th. Okay, so that's my top piece in parentheses. Then I'm going to divide my bottom piece, which was 10 to the 4.40. Oops, delete that. And make sure we close off all of our parentheses. So I got to close off the parenthesis from the 10, but then I also got to close off the parenthesis from the log. So really simple plug and chug into your calculator, looks like 6.48 about. So we can write, the magnitude would be 6.48 joules of energy. You're probably hoping Miss Bites can't all these be that way? Alright, so what I want you to do is pause the next 2 and try those on your own. Notice how number 12, how many years will it take $5,000 to amount to $8,000 if the interest, or if it's invested at an annual interest rate of 9% compounded continuously. So we're going to use that continuously compounded interest equation, okay, aka PERT. And just as a refresher, I tell you what each piece means. So go ahead and try this one, as well as 13. 13, we're dealing with carbon dating. Okay, we're trying to figure out how old a sample actually is. So go ahead and try 12 and 13 on your own, and I'll be back in a little bit to see how you do. Alright, so let's check it out and see how we did. Using our PERT equation, A is the amount in the account. Okay, so we eventually want $8,000 in our account after we let it sit in there for a while. So we want $8,000 eventually. P is the principal, or what we initially put in, which would be that $5,000. And the rate in this case is 9%, but remember we got to write that as a decimal, so 0.09. And we're actually trying to figure out T, okay, how many years. We're trying to figure out a time frame, so that's our variable in this case. So notice how we have an exponential, we have a exponent in the power or exponent position. So let's isolate that exponent. We can divide the 5,000 over to give us that 1.6, and now that it's all by itself, we can convert to a log. Now since the base is e, that means we have to use a natural log of 1.6, and that should equal our power of 0.09t. So from here, we can calculate the natural log using our calculator. It would give us about maybe 0.47. And when we divide the 0.09 over to get a value of t, we're going to have to wait about 5.2 years. So when you put this much money into a bank account that's earning 9% interest, you can expect a little bit more than 5 years in order to raise your bank account from $5,000 to $8,000. So this is a really handy formula. Okay, exponentials and logarithms are very useful, especially in this case when you're dealing with money. Okay, I think that's pretty precious to all of us, especially in the future. Alright, let's see how we did on this last one. This one can be kind of tricky. Not sure if you kind of caught what was going on here with the percentage, but let's just go ahead and talk through this one. In 2004, archaeologist Al Goodyear discovered a site in South Carolina that contains evidence of the earliest human settlement in North America. Carbon dating of burned plant material indicated that 0.2% of the amount of carbon-14 was left in the sample. Okay, so we're trying to figure out how old is this sample. So how old is this evidence of the oldest human on North America? So what carbon dating does is it gives us a way, especially in biology in this case, to date objects. It could be human evidence, it could be plant evidence, it could be rock evidence, but the scientists analyze the different carbon atoms and to figure out how old something actually is. Now in our little formula here for carbon dating, the A represents the amount of carbon in our evidence or specimen after a certain time, and A sub 0 is the amount of carbon that was initially or originally in the item or evidence, okay, kind of like at time 0 at the very beginning. So we kind of had to use this information of 0.2% to help us figure out those A pieces. So this is 0.2% of the carbon that was left over. Okay, now we can write 0.2% as a fraction. Okay, since it's a percent, we can put it out of 100. Now if this 0.2 is what's left over, okay, that's what was left in 2004, that means the 100 is kind of how much carbon this evidence or this piece that was discovered, that's much carbon it started with. So it's left with 0.2, which means it originally started with 100 because they're giving us this information in a percentage form. So if there's 0.2 left, that's what would go in the A position because that's how much is left after a particular time frame. Now, in this case for the A sub 0, the amount that it originally started with would be the 100. So we kind of had to analyze this percentage to help us figure out those two different A values. Now, since we're trying to figure out how old the sample is, that's what we're trying to isolate our variable of time. So notice how t is in the exponent position. We want to get the exponential all by itself. We can divide the 100 over to give us the 0.002. And now that our exponential is isolated, we can convert it to a log. Again, since we have a base of e, we need a natural log of 0.002, and that should equal our exponent, this long bad guy right there. So using our calculator, we can find the natural log of 0.002 to be about negative 6.2146, and to divide this negative decimal over to isolate t, this sample of the oldest human settlement in North America looks to be over 5,000 years old, okay, based on our algebra and our logarithms and our exponential equations. So carbon dating gives us a way to date back ancient items based on the amount of carbon they have in the sample. So hopefully we're doing pretty well with these word problems. It's just using a formula and then our math skills to help us answer the question. So go ahead and try those practice problems and that application. Most of all, good luck on the mastery check, and I'll see you guys later.